helical antenna here. As nothing but here is it's a kind of an antenna here, which is able to emit or generate the radiations here and respond to whatever the electromagnetic field here with the circular polarization here. Okay, we'll be having three kind of polarizations here, like vertical polarization and horizontal polarization and circular polarization. No, sorry, elliptical polarizations will be there. So there are many different kind of polarizations we are having here, but this is the one helical antenna here, which is going to radiate and respond here to the circular polarization here. Okay, now how exactly this particular antenna looks like, or what exactly it consists of here. Now it is just conducting wire here, okay, wound in the form of a helix here. Helix is nothing but like a cylindrical form here. You can see in this particular diagram here. Okay, this is what is our helical antenna here. Okay, so helical antenna consists of what here? The conducting wire. This is the conducting wire here. Okay, just I'm showing with the mouse pointer here. This is what is conducting wire here, which is wound in a, what you can say that, in the form of a helix here, right? Okay, which is mounted on a metal plain ground here. Okay. Okay, so this is how it looks like now. This is how, what is the conducting wire here, which is wounded in the form of a helix here. Okay, or you can say this particular conducting wire, which is wound on a cylinder here. That is also nothing but here you can consider as helical antenna here. Okay, now where exactly the feed line is connected? Feed line is nothing but here your power supply has been connected here. Power supply is connected between the, what you can see, the bottom of the helix here, and this is the bottom of the helix here. See, again I'm showing with an pointer here. This is the bottom of the helix, and whatever the metallic plain ground, between these two things our power supply will be connected here. The feed line is nothing but here power supply, or you can say transmission line here. Okay, so this helical antenna operates in two modes here, as it has been given here: normal mode and axial mode here. Okay, so we are going to discuss in detail regarding the normal mode and axial mode here, but remember only 2 points here, just for our clear cut understanding. Or see, usually in the normal mode, or you can say that it is in a broadside mode here, what is going to happen here is whatever the radiations that has been generated now, it will be exactly perpendicular to the axis of the helix here. Remember, the radiations, or you can say the maximum radiations that is being generated by the helical antenna, okay, will be perpendicular to the axis of the helical antenna here. That is what is will be there in the normal mode here. Quite opposite will be there in the axial mode here. What is going to happen in axial mode here? Whatever the maximum radiation that is going to be generated by the helical antenna will be along the axis of the helix here. Okay, that's why it is also called as the end fire case here. Also, I think you have learned in the previous classes again the broadside and end fire case. No, so broadside is nothing but here perpendicular to the axis here. End fire is nothing but here along the axis here. Okay, that's why whatever the maximum radiation that has been generated by the helical antenna, if it is perpendicular, it is a normal mode. Okay, if it is along the axis, it is called axial mode here. Okay, and remember here, whatever the dimensions we are having in the normal mode, it will be small. Okay, very small compared with the wavelength here. Okay, and in this axial mode here, axial mode, the circumference c, okay, circumference c will be order of one wavelength here. Okay, this much difference you remember here in the initial stages here. So let us discuss the exactly the structure of this particular helical antenna here. I think you have seen this diagram just now. So what exactly this diagram is? It is a three-dimensional geometric form. It is in the form of three-dimensional geometric form here. Okay, so just a uniform cylindrical cylinder here becomes a straight line here. Now, so if at all what we do here is, if at all we stretch, okay, is whatever the helix wire that is being wound on the cylinder here, if we stretch that particular wire here, or unwound the wire here, then it will become a straight wire here. Okay, up on the flat surface here. Okay, now how exactly, if at all the helix is there, which is wound on in a helical format, or the wire which is wound on the cylinder here, if you look in the top view, or you can say top view, if you look here, it just looks like a circle here. Okay, that means here, if at all you look from the end of this helix axis here, it just looks like a circle here. Okay, that's what he wanted to say. So what is exactly this helical geometry is something, but it is a combination of straight line, a circle, and a cylinder here. Remember, helix antenna is a combination, okay, in geometry form. Okay, that too, straight line, a circle, and a cylinder here. So what are the parameters that we have here? Or you can say, I told in the normal mode here that the dimensions of the helix are very small. Dimensions, we are trying to understand the dimensions here. These are the parameters that are related to what is helical antenna here, right? So what are the parameters we are having here? Capital D is what is capital D? Diameter of the helix here. C is nothing but here circumference of the helix here. S is nothing but here space between the turns here. You see, this is the diameter of this capital D. It has been mentioned here, right? So this is the diameter of the helix here. So C is nothing but here circumference here. Circumference of the whatever the helix is there here, right? Okay. So spacing between the turns here. So this particular this is the yes, it is been represented here, right? This is nothing but here spacing between the turn. This is regarded as a one turn here. Okay, one turn, length L is equal to one turn. This is one turn here. Spacing, this is another turn here. Okay, so spacing between the turns here. Pitch is nothing but here. See here, alpha is nothing but a pitch angle here, right? L is nothing but, as I told, this is the length of one turn here. Small n is nothing but here number of turns here. How many number of turns here? We are having around three turns. We are having 1, 2, 3. Okay, 1, 2, and 3. So actually is nothing but here whatever the number of turns are there into the spacing between the turns will give me the actual length here. Small d is nothing but a diameter of the helix conductor here. Okay, just a minute. Okay. So the diameter d and circumference c refer to the imaginary what you can say the cylinder whose surface passes through the center line of the helix conductor here. Okay. So whatever the diameter is there, it will be expressed if it in terms of the lambda here, or you can say the wavelength say that will be represented by capital D suffix lambda here. This is the helix diameter in a free space wavelength here. Okay, where lambda subscript signifies the dimension measured in the free space here. Now, if at all we take this one turn here, okay, one turn of whatever the circular helix is there, okay, if we unroll it, okay, on a flat plane here, the relationship between whatever the spacing is there, or the circumference is there, or the length is there, and the pitch angle can be shown in this particular figure here. So you can see in this particular figure here, whatever the one turn is there here, which is wound on a cylinder here, or in the form of a helix here, which will be unwounded here, or you can say unrolled here, make into straight line here. If at all we make it here, then this is how it looks like now. Okay, so it is a exactly right angle triangle here. Now the spacing, if at all we consider as a zero here. Now what is yes is nothing but here space between the turns here. If at all we consider the space between the turns is equal to zero, so what is going to happen now? Alpha, that is nothing but a pitch angle, is equal to zero. Obviously, if this s is equal to zero, we don't have any kind of a length here, then alpha is equal to obviously zero, and then this helix becomes the loop here. Okay, helix becomes the loop, just circular loop here. Now if at all we consider that whatever the diameter is there, capital D, okay, capital D diameter is equal to zero, that is nothing but in this figure you can see capital D is there here, right? So if this diameter is equal to zero, that we don't have any kind of a diameter here, then it will be obviously a straight line conductor here, right? If D is equal to zero, then circumference is equal to zero. So what is going to happen now? Alpha is equal to 90 degree, alpha is equal to 90 degree, and whatever the wire is there, it will be just a thin linear conductor here, right? Linear conductor here. So this is how we can state regarding if at all, if we take one turn of a circular helix and it is unrolled here on a flat plane, if spacing between s that is turns is equal to zero, that is s is equal to zero, obviously alpha is equal to zero, then it just looks like a loop here. If at all the diameter d, capital D, is equal to zero, then circumference is equal to zero, then we can say that it is a linear conductor here, right? Now there are two modes are there here. helix modes here. That is one is transmission mode and radiation mode here, which uh, the modes of the helix can be described. Two terms, two modes are there here. Now let us discuss the first mode here. That is normal mode helix antenna here. Now what is going to happen in this normal mode of helix antenna here? Whatever the length is there, okay, that is nothing but L is equal to uh, the length of one turn is there, no? That is very much less than the compared to the operating wavelength here, or whatever the diameter we are having, no? Capital D, okay, that is also very small, okay, or very less comparable to the wavelength here. Okay, if this is what will be there here, then the efficiency is also will be low here in this case here. Remember here in the normal mode helix antenna here, the dimensions are very small here, okay, and whatever the dimensions are there, it is very much less than the what you can say operating wavelength, hence its efficiency will also be low here. Okay, now in the normal mode elixir, as I said in the initial part of the helical antenna here, whatever the maximum radiation is being generated here, it is what you can say that it is perpendicular to the axis here. That is helical axis here, and whatever the polarization effect we are going to get, it is always a circular polarization. There is no electrical polarization or vertical or horizontal polarization here. Right now, whatever the assumption that we are having, or in the normal mode helix antenna, all the dimensions are very small here, and hence helix is very small, so efficiency is also low here. Because of this one, what is going to happen, whatever the current is there here, okay, the current is assumed, or it is very constant here, or I can say that constant in magnitude and also phase over its length here. Okay, so now with this thing, what we can say is that whatever the field pattern that we are going to get from this particular number of terms here, okay, yeah, number of terms n is representing the number of terms here, okay, number of terms here, so it will be equivalent to what you can say is exactly one term here. So if at all we find out the far field pattern of one turn is equivalent to the far field of n terms here. That's why we say that far field pattern is independent of a number of terms that we are having here. Okay, so because of the because of its very small in dimensions here. Okay, one turn, how exactly the one turn could be represented here. Okay, one turn can be approximated as a small loop here. Okay, so as you can see in this particular figure here, the far field electric dipole, uh, okay, can be directly taken as e theta. E theta is equal to j65 into whatever this square bracket I is there, no? That is nothing but a retarded current here. I think we have discussed in the previous classes here, retarded current into sine theta divided by r into s divided by lambda here. S is nothing but here spacing between the helical turns here, right? Okay, if at all the far field electric field of a small loop is considered, this is the electric field that has been considered for what here, the dipole here, direct equation here. If at all we consider a small loop here, so that also we are having this equation here, that is E5 is equal to 120 pi square sorry into whatever the retarded current we are having here, that is square bracket into sine theta divided by r here, a divided by lambda square here. Okay, so now there is we need an explanation for this particular a square here, so that's why we are switching to some other document here. Let me switch to some other, because one page is missing here. So 11, page number 11 is 11 12 11 after 11 there we are having 12 here, but there is one page that is been missing here. I'm just going to go to that particular page here, just for a second here. Okay, this is okay, this is what is missing here. 11.1 page is missing here, so I'll just continue from there here. See here, E5 is equal to what has been given here, far field. We have found out what here, far field electric field of a dipole we came to know here, and far field electric field of a small loop we came to know. So where a is equal to pi d square divided by 4 is nothing but here area of the loop here. Remember, where E is nothing but here capital E, which we have written here in this page number 11 here. Okay, that is nothing but here area of loop here. So the ratio of electric field components is given by the axial ratio here. So that is what we wanted to find here. Okay, axial ratio. Okay, how do you find here? Ratio of whatever the, okay, this electric field components, that too from the dipole and the small loop here. So we are taking this e theta magnitude and e phi magnitude here. So at last we are having the value of s into lambda divided by 2 pi into a here. Okay, so you know the value of a here. A is nothing but here, what you can say that, uh, what to say here, a is nothing but the area of the loop here. So we can substitute the value of a here, that is pi d square divided by 4a. If you substitute, you will be having the final value as 2s into lambda divided by pi square and d square here. Okay, this is what we are going to have as axial ratio here. Okay, now let us understand here axial ratio. Suppose if we have axial ratio always ranges from 0 to infinity here. Now when we consider as s is equal to 0, s is equal to 0 is nothing but here we don't have any kind of a spacing here, right, between the turns here. If we don't have any spacing between the turns here, then the axial ratio is equal to 0. Okay, correspond, which is nothing but here, as I said in the just now 15 minutes before it, if it is s is equal to 0, it will going to act as a just a loop here, so small loop here with horizontal polarization here. If at all we don't have any space between the turns here, then axial ratio is equal to 0, and hence it will act as a small loop here, which will be having the horizontal polarization here. Now if we consider the diameter is equal to 0 here, okay, so if at all we consider the diameter is equal to 0, then if at all we consider the capital D, that is diameter is equal to 0, diameter of the helix is equal to 0, then axial ratio is equal to infinity here. Okay, so if at all as I said in the previous just 15 minutes before discussion here, capital D is equal to 0 means what it is going to, it is going to act as a linear conductor here. Okay, or I could consider the short dipole here with vertical polarization here. Now when exactly the circular polarization is going to have here, because the initial definition we have said that it is going to emit and respond electromagnetic field with circular polarization. Okay, okay, what it is, a helical antenna is a specialized antenna here, okay, which is going to generate certain radiations here, and it is going to respond to particular whatever the electromagnetic field is there with the circular polarization. That's what we have described in the initial stages here. So if at all we wanted to have the circular polarization in the helical antenna here, your axial ratio, okay, ar, capital ar, this should be capital A here, so the ar should be equal to 1 here, unity. Okay, so this AR is equal to 1. That is nothing but here 2 S into lambda divided by pi into pi square into d square here. That is, so we can write here. Okay, that is pi into d square is nothing but a c square you can write here. Okay, c is equal to root of 2 S lambda here. Okay, now let us go to that particular figure B here. I think we have written here figure B. That is this one here. So if from the figure B here, this is nothing but here your right angle triangle here. So if at all we wanted to find the sine alpha here, what is the value here? Sine alpha is nothing but here s divided by L. You can see here s divided by L here. Okay, adjacent divided by hypotenuse here. Now again regarding the alpha here, okay, so alpha is nothing but here, that nothing but pitch angle here, sine inverse of s divided by L here. This could also be written as, okay, which both are same here. Sine alpha is equal to s divided by L, or alpha is equal to sine inverse of s divided by L here. Okay, you know the Pythagoras theorem here, or Pythagoras equation here, c square plus s square is equal to L square here. This is okay here, c square okay, plus s square is equal to L square here. Okay, now after that, what is going to happen? Okay, so now the radiation resistance here, in this case radiation resistance for a normal mode of helical antenna is given as 640 into h divided by lambda whole square here. Okay, this is what is the radiation resistance. We need not to derive this particular radiation resistance here. As per the syllabus here, you just need to mention the equation here. R is equal to 640 h divided by lambda whole square here. Now let us move on to the next particular thing here, that is axial mode. We'll move on to the previous PDF here. Just a minute. Yes. Okay, so now the actual mode, the helical antenna here. Now, as usual, we have described here. So what it is now in this particular actual mode here, whatever the helical antenna that is going to generate certain radiations here, okay, which will be along the axis here. So it is also called as a what you can say that end fire helical antenna. Also, you can say that because single beam will be there along the axis of the helical antenna here. And remember here, whatever the radiation that has been generated here, it will be very close to the circular wave, like polarized near the axis here. Okay, and remember here, if at all we are going to operate our helical antenna in the axial mode here, it will be having a gain up to 15 dB here. Okay, and has because of the relatively very small cross sectional area here, it is a very popular antenna, popular helical antenna in the ultra high frequency here. Okay, which is very widely used in the satellite communications here. Okay, and remember here in this case here, circumference